Oops. All right. Good morning, class. This is lesson 14, covering section 4.1 of our textbook. So we have finished chapter 3, and we're now transitioning into chapter 4, where in chapter 4, we're really going to get into the nitty-gritty detail of what does it mean to be a vector space, right? So far we've talked kind of abstractly about some examples of vector spaces. For example, we've talked about places like R2, where we said, you can have a vector in this space, and it looks like this, right? So we have these vectors in R2, and R2 can be written as a vector space. In fact, R2 is an example of a vector space. In some ways, it's kind of like a first simple example of a vector space. It's what people usually think of. This is the vector space that is typically worked with in physics. But again, depending on your application, this might not actually be an appropriate space to be working in. But we've also seen, you can also have R3, R4, R5, so on. These are all vector spaces. R to any n is a vector space. And in fact, you could also say R to the naturals. You can imagine where this power is stating how many axes, how many different directions you can move in, right? For R2, there's an X and Y axis. For R3, there's an X, Y, Z axis. For R4, there's 4 axes. But for R to the naturals, this is a vector space where you have, so the naturals, what is that? That's an infinite set. That's the set 1, 2, 3, 4, 5, 6, 7, 8, 9, blah, 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 so on and so forth, right? So this vector space is actually one which has infinitely many axes, and so it is an infinite dimensional vector space. So all of our examples we've looked at so far have been these finite dimensional spaces. R2 is 2-dimensional, R3 is 3-dimensional, R4 is 4-dimensional, right? But we are not limited to just finite vector spaces. We can also talk about infinite vector spaces. Now, I'm stating this really just as like a brief introduction. The point of this class, since this is an introductory linear algebra class, we're not going to spend a lot of time talking about infinite dimensional vector spaces, just because they're a little bit beyond the scope of this class. They work a little bit differently. They're kind of funny. Strange things happen there. For the sake of this class, we're going to be talking about finite dimensional vector spaces. All right. So we have these examples of vector spaces, but what actually makes a vector space a vector space? What's special about R2 that makes it a vector space? So that's what we want to talk about next. So definition. Let V, capital V, be a set of vectors. All right. Then V is a vector space. So generally, we're going to use capital V for vector spaces. V is a vector space if the following happens. For any UV, so these are lowercase u and v. In V, so these are vectors. Lowercase u and v are vectors. And for any constant scalars, C, D, in R, C and D are constants. They're fixed real numbers. So if for any u and v and for any C and D in R, we have, first of all, 1, u plus v is in capital V. So basically, we're just saying, first of all, if I add 2 vectors together, I want the result of adding together to still be in that space, right? There are some weird examples of things where it's not a vector space. For example, you could imagine like, well, what if I say V is the set of vectors in R2 such that x squared plus y squared is less than or equal to 1, right? What does this mean? Well, you might be familiar with this equation. X squared plus y squared equal to 1 is the unit circle. That's a circle centered at the origin with a radius of 1. But when I say less than or equal to, this is saying any xy point, which is on that circle that's with a radius of 1, or any point that's less than 1. So this is any point in the unit circle, inside of the unit circle. Okay. But is this space I've described a vector space? Well, no. Why? You can imagine if I take 1, 0 and add it to 1, 0, I'm going to get 2, 0, which means it's possible to add two vectors together and get outside of the set, get outside of the space, right? So V, this example V, is not a vector space because I can add two things together in here that get outside of it. And so that's not going to be a vector space. R2 is a vector space because no matter what two vectors you add, it's still in R2. So that's the first requirement. Number 2, we're going to require U plus V equals V plus U. We need to have commutativity with the addition operation. Now, generally speaking, if addition is using like the traditional definition for addition, if it's using addition how we expect addition to work, we know from like regular real numbers, addition is always commutative. This kind of rule is pretty much always going to be a given for free. You're pretty much always going to have this one. The only time 2 might break is if you're working in some kind of set where they give you a definition. They say, well, when we add two things, we actually mean something else, right? So that would be an example where their plus sign is represented as something else, which is not like the traditional plus sign. We're not going to worry about examples like that in this class. This is mostly just a heads up that if you were to go further in linear algebra or in physics or these other more advanced topics, sometimes this plus sign might be a different operation than the plus sign we're used to. But so long as it's the usual plus sign we're used to, number 2, we're going to have working for us. All right. The same can be said for this third rule. This is usually going to be true for any regular plus sign operation. If we have U plus V plus W, then I would like to be able to associatively move the parentheses. And regular addition does have associativity, so I can move the parentheses, and this is going to work most of the time. Again, this is only going to break if your plus sign operation is something different than the usual plus operation we're used to. All right, so 2 and 3, not such a big deal. 1, that one's pretty important. Okay, number 4, we want to say that there exists a 0 vector, this one's key, in V such that 0 plus U equals U, and it doesn't really matter which order we do this in. If I add 0 to a vector, I'm supposed to get back the original vector. This one can be key because depending on what set you have, the 0 vector might not be in there. For example, you could imagine, well, what if my set V is a set of vectors that's inside this box I just drew, right? Well, if it's inside this box I just drew, then you can see quite clearly just by looking at it, the 0 vector is not included in that box, right? There is no 0 vector inside that set, which means there's no zero vector I can add to things so that I get back the original vector. To be a vector space requires that you have this additive identity element, meaning we're requiring there be something that if you add it to other things, you just get back the thing you added to, right? But that can only happen if the zero vector is in your set. So number 4 here is key. I'm highlighting the ones that are kind of more important that you can use to check whether a set is a vector space or not. These are usually going to be the go-to things you want to check for. All right. Okay. Of course, there's more to the list here. Secondly, we want to require, now this one can also be key. You're not going to have this happening all the time. For any u, in V, there exists a negative u in V such that u plus negative u equals 0. And again, the order doesn't matter here. We already know that from number 1. The order in which, or sorry, number 2, the order in which we add vectors doesn't matter. We should get the same thing. So what is this talking about? Basically, for any vector, I want a way to add something to it that allows me to get back to the identity. So it's not enough to have the zero vector in your set. You need to have a way to add vectors to other vectors so that you can always get back to it if you want. So you can think about, you know, a set like this that I've just drawn on the board. This is including these vectors which are on the right side of the x-axis, right? Or actually, better yet, let me give you this example. Let's suppose that V is quadrant 1. It's quadrant 1, right? So everything in quadrant 1, okay? All the vectors in quadrant 1, their x and y are positive, right? So there's no negative vectors in quadrant 1. So if I have a vector, let's say like 1, 0, is there anything in quadrant 1 I can add to it that can result in the 0 vector? Well, the only way to get it to the 0 vector was if I could have something to cancel out that 1 in the x entry. But in quadrant 1, there are only vectors with positive entries. There's no way I can subtract from this x. There's nothing I can add to 1. There's no positive number I can add to 1 that will result in 0. So this example where I have an infinite set of vectors in quadrant 1, this is also not a vector space. Why? Because I don't have these inverse vectors. I don't have inverse vectors I can add together that results in 0. So this is also number 5, a key point you want to highlight for vector spaces. Okay. 6. And this one's also key here. So remember, we're saying for any vectors in V and for any constants, C and D in R, we want CU is in V. This one's also important. We're saying if I take a vector, I want to be able to multiply it by any scalar I want. This is any constant real number. I want to be able to multiply it by any real number I want, and I want the result to still be in the space. Well, again, this example up here is going to fail, and it's going to break number 6, right? How is it going to break number 6? Well, if I multiply it by, let's say, -1, well, then I get the vector -1, 0, right? This is -1 times 1, 0. In other words, there was a way for me to multiply a vector by some scalar such that C times that vector is no longer in the set, right? So then CU is not in V. This is not a vector space because it breaks 6. It also breaks 5. The rest of these it's okay with, but it breaks 5 and 6 here. Why do we care that a vector space can do these things? Well, think about everything we've been doing up to this point in the class. For everything we've been doing, we need vector spaces to be able to have linear combinations, right? A lot of our questions are things where we're talking about what are all the possible linear combinations, or we ask, is some vector B a linear combination, so on and so forth. So in order to be a vector space, we need to be able to talk about linear combinations. In order to talk about linear combinations, well, first of all, I'd better have all my combinations for adding them together in the space, and I'd better have scalars of vectors in the space. If I can't add things together, if I can't scale things in there, then I can't take linear combinations. It's not going to work for what we're trying to solve. So we require these for vector spaces so that we can really get at these problems about linear combinations. Okay, so this is number 6. There are some other properties. These are not as important. They're ones that are generally going to be true. Predominantly 1, 4, 5, and 6 are the big important ones. These are the ones you're generally going to try to check for to see if something is a vector space or not. So again, 1, 4, 5, and 6, these are the key ones you really want to try to remember for what makes a vector space a vector space. All right. Now, in order to finish this definition, I'm going to have to erase some of this. We have a few other points that are required for a vector space. All right. And we've seen some examples of things which are not vector spaces. And we'll also talk about other examples of vector spaces besides R2, R3, R4. Okay. So next, number 7, we want to be able to have the distributive property. And again, if we're talking about regular addition, the way we're used to addition working, then generally speaking, you're going to have this distributive property. This isn't usually going to be something that breaks. This is something you're usually going to have. This is something you have to really pay more attention to if you have some kind of weird addition operation, which works differently from how we're used to. Okay. For 8, again, another distributive property. If I have 2 constants being added together with a vector outside, I'd like to distribute that vector. So again, this is going to work pretty much all the time. This one's not going to be a concern. For 9, we'd like to have associativity when I'm multiplying scalars, just like we had when we're multiplying scalars on matrices, same kind of idea. And again, this is something we're usually going to have no problem. And lastly, if I multiply a vector by if I multiply a vector by 1, a constant 1, I want to get the vector back. Now, this is something where, yeah, if multiplication is your regular, typical scalar multiplication we're used to, then this is always going to happen for free. The times that 10 is going to break is usually when your multiplication works differently. When you multiply by 1, something weird is happening with your multiplication, something else is happening. Again, for the sake of this class, we're not going to look at those kind of things, so don't worry about that so much. Again, the key points we want to highlight was number 1, 4, 5, and 6. The rest of these kind of things, while they're all required for a vector space, for all the examples we're looking at, these are things which are generally going to be true pretty much always. So we won't have to worry about them as much as those others. Okay, great. So we have this definition for a vector space, and we've looked at some counter examples of things which are not vector spaces. Okay, so what else can we do with vector spaces? Well, on one hand, we might be curious about, what if, for example, I don't care about all of the vector space. Maybe I only care about a portion of the vector space. I only care about a portion of the vector space which applies to the linear combinations I'm thinking about. So what happens here? Well, we have this notion of things which are called subspaces. What is a subspace? Well, first of all, it's a subset of a vector space. So let H, this notation just means subset. Let H be a subset of V, where V is a vector space. Okay. Then H is a subspace of V if the following happens. Number one, to be a subspace, so first of all, to be a subspace is a type of vector space. It's just a vector space inside of a vector space, right? It could be a smaller vector space inside of a vector space. But the first requirement is whatever this subset is, if it's going to be a subspace, in other words, if it's going to be a smaller vector space, it also has to have the zero vector. So the zero vector in V, whatever that zero vector is also in H, right? So H also has to have the zero vector. 2, we're also going to require, like before, for any two vectors, U and V, in V, U plus, oops, sorry, not V, in H, right? For H to be a vector space, we don't want any way to add two things together so that we escape the space. So when we add two vectors, that also has to still be in H. And then lastly, for 3, for any U in H and any constant C in R, C times U is in H. Again, we don't want any way to be able to multiply my vector by something and it result in something which is outside of the set. If that happens, it's not a subspace. But note, I only have these 3 things to check. I don't have to check the rest of those 10 things we just listed for a vector space. Why? Well, because H is a subset of V, well, if V was a vector space, that means a lot of those properties also work for H automatically, right? So really, what do we have to check? Well, 1, we got to check the zero vector is still in there. 2, we got to check if I add things together, it stays in there. And 3, we got to check if I scale a vector, is that still in there, right? In fact, this is what is called the subgroup test. Subgroup test, right? You check these, or sorry, not subgroup, subspace. Subspace test. Subgroup is a different thing. That's for a different math class. Subspace. This is a subspace test. You check these 3 things, then lo and behold, that thing is a subspace. But we've already seen examples of things which break this. For example, again, if you think about the unit circle, right? You can think about H, which is the set of vectors in R2. So H is a subset of R2 such that x squared plus y squared is less than or equal to 1, right? We have the zero vector in there, so number 1 checks off. But for vectors I add together, it doesn't stay in here. If I add 1, 0 to 1, 0, I get 2, 0. That's out of the space. Similarly, scalars don't work. If I have 1, 0 and multiply it by 3, that becomes 3, 0. And now that's out of the space, right? So H here is not a subspace precisely because it breaks 2 and 3. Since, for example, 3 times 1, 0 equals 3, 0 is not in H. And let me make sure I didn't run off the screen there. Oh, good, just barely. All right, great. So this is how, in general, we're going to tell if something is a subspace or not. For this example, H, it is not a subspace. Okay? So let's next try to look at some examples of things which are subspaces. And in general, how are we going to tell? Well, in fact, we're going to find out that sometimes there are quicker, easier ways to figure out if something is a subgroup, or sorry, subspace. But we're gonna look at that. Okay, so examples. First, let's just stick with a simple example. Let's suppose, well, first of all, let's let V equal R2. Right? So V is a vector space we're used to, and it's a vector space that's easy for me to draw on the board. Let V equal R2, and let H equal the span of the vector 1, 0. Okay, what is this? Remember, span is the set of all possible linear combinations, right? It's an infinite set. It's an infinite set of all possible linear combinations, except in the case of this example, I only have one vector in here. Well, when you're trying to take linear combinations of a single vector, all you can do is just scale it, right? So this is the set of all possible scalars times 1, 0, such that C is in R. Again, this is an infinite set. So what does this set even look like? Well, if I try to graph this, we know, okay, well, it has the vector 1, 0, right? But it also has any scalar of it. If I double it, okay, well, it has that vector. If I triple it, okay, it has that vector. I can multiply it by -1, -2, -3, right? I can multiply it by fractions. I can multiply it by irrational numbers. I can multiply it by any constant I like, and it's going to fill in. It's going to fill in the entire y-axis, right? This is what the span of 1, 0 looks like. It is the line x equals 0, right? This is what the set H looks like. Notice, just by looking at it, this includes the 0 vector. So number 1, check. It has the 0 vector. Why? How do we know it has the 0 vector? Well, I could let C equal 0. Then 0 times 1, 0 equals 0. And because the span is a set of all possible linear combinations, that means the span of 1, 0 has this combination. And so this means that the 0 vector is in H. Great. So 1 is checked off. What about 2? We want to be able to add any vectors together, and we want them to still be in the set. Is it possible to add 2 vectors together, which we'll get off of this line? Well, we can check. So first of all, let U and V be in H. So notice, in order to prove that number 2 works, in order to prove that this set has closure under addition, if I add things together, I stay in the set, I stay in the space, I have to let u and v be arbitrary, right? I can't just pick examples of u and v which work and say, oh, aha, it's a vector or it's a subspace. No, that doesn't work. If you do that, you will lose points. U and v must be arbitrary because we have to show that no matter what u and v are, if I add them together, it's still in H. So because of that, it has to be arbitrary. Okay? Well, if u and v are in H, this means that there exists constants, I'll call them C and D, in R such that u equals C times 1, 0, and v equals D times 1, 0. In other words, the fact that they're in H means u and v are both in the span of 1, 0, which means they are both a combination of 1, 0. Okay, but now what happens when I add them together? Well, u plus v is going to equal C times 1, 0 plus D times 1, 0. Now, what's nice here is that these vectors are in a vector space, which means we have access to all of those properties for a vector space. I can factor out this vector 1, 0. In other words, this is just C plus D times 1, 0 here. Right? C plus D is just some real number constant, right? C plus D is in R. So what have we shown? We've shown when with an arbitrary u and v, when we add them together, that's really just a combination. It's a linear combination of 1, 0, right? In other words, u plus v is in R. U plus v, so therefore, and I'll use this notation with these 3 dots and a triangle symbol. This just is a shortcut symbol that means therefore. Therefore, u plus v is in H, which is what we wanted. And then lastly, the third thing we require is that C times U is also in the space. Well, again, U has to be arbitrary. Let U be in H. And the scalar I'm using has to be arbitrary. Let C be in R, right? So it's an arbitrary constant. Then U in H implies what? Well, it implies that U is in the span of 1, 0, which means U is a combination of 1, 0. So there exists a D in R such that U equals D times 1, 0. Okay? The very last thing here, though, is that we want to check, well, what is C times U? We want to check if I scale this arbitrary vector U by an arbitrary constant, what happens? Well, C times U then is C times D times 1, 0. But C times D is really just some constant. It's just some real number in R. So C times U is just a scalar of 1, 0. It is just a combination of 1, 0. And in fact, we get, therefore, Cu is in H. So we checked all 3 properties. And therefore, we can say, by definition, H is a subspace. Right? So this is something nice. Here's an example. And it's an example which this is not all of R2, right? This is just a single line in R2, but it has a 0 vector. It has all of these combinations. Why do we know that it has all the combinations? Because that's the definition of span. In fact, anytime you have a set which is the span of some vectors, that set is always going to be a subspace. Why? Well, you could always take a linear combination where you make all of the scalars 0. If you make all the scalars 0 and add them together, just like we did here, you're going to get the 0 vector. So for any set which is the span of something, that automatically has the 0 vector. Okay? What if I add two things together? Well, again, by definition of span, for any two vectors that are in here, H includes those combinations. H is the set of all possible linear combinations, which means it's always by default going to include U plus V. And similarly, if you scale a vector, that's also going to be in the span because, again, that's a linear combination, right? So this actually, while we did the work to prove it here, in practice, we can actually use a theorem here, which can make this problem a little bit faster and shortcut it. So we have a nice theorem here, which says, theorem, let V be a vector space, and let V1, V2, ... Vn be vectors in V. Okay? Now here's where the magic is. If H equals the span of these vectors, then H is a subspace of V, right? And in fact, this is going to happen every single time. Why? Well, again, the span includes all possible linear combinations. So you can take the linear combination where you scale everything by 0. That gives you your 0 vector. You have all the possible ways you can add vectors together because the span is the set of all possible linear combinations. And you have all the scalars because, again, the span is the set of all linear combinations. Any set which is the span of something is always going to satisfy those 3 points for a subspace. So anytime you can rewrite a vector, or sorry, a set H as the span of something, then you automatically have a subspace. So sometimes this is a quicker way to check if something is a subspace or not, instead of checking those 3 things, those 3 properties. All right? So I want to show you an example of that, how using this theorem can help shortcut things. How does this work? Well, now let's make things a little bit trickier. Let's say V is now the vector space R4. That's still a vector space. It's big. It's a 4-dimensional vector space, but still a vector space. And let H equal this set A minus 3B, B minus A, B. This is a vector in R4 such that A and B are in R. So what is this saying? This is saying let H be the set of all possible vectors where you pick whatever your favorite real numbers are. You can pick infinitely many of them, right? For any real numbers A and B, if they add together in this way to create a vector, then H contains this vector. Okay. Now this seems a little bit tricky. There are 2 ways to kind of check if H is a subspace or not. Is H a subspace of V? All right. Well, number one, you could try to very carefully go through checking those three things. I mean, first of all, you could say, well, it looks like if you make A and B both 0, then you get the 0 vector. All right, great. So the 0 vector is in there. That helps. But now when you want to check for an arbitrary u and an arbitrary v, if you add them together, what happens? Do you still have something in H? Well, the trickiness there is that if you pick an arbitrary u, okay, that means there's some a and b which make that u. But if you have some second arbitrary vector v, it would be a different a and b which make that v, right? So you have to use letters like c and d. Well, now when you add them together, you have 4 different letters running around, and that can get very confusing very quickly. All right, so instead of going down that rabbit hole, what else can we do? Well, notice, what is this vector? What happens if I pull it apart into parametric vector form, right? Don't forget about that idea, because parametric vector form is going to be very important as we continue in the class. Well, if I pull this apart, I have a times 1, -1, 1, 0, plus b times -3, 1, 0, 1. Right? In other words, what is this saying? A and b are any possible real numbers. In other words, what is this vector? This is a linear combination of these two vectors. In fact, it's any possible linear combination because a and b can be any real numbers. So what is H then? H is the set of all possible linear combinations of these two vectors. In other words, while it was written this way, it turns out H is actually the span of 1, -1, 1, 0, -3, 1, 0, 1, right? H is the span. Well, then therefore, by that theorem we just had, and in the textbook, it might give you like some kind of number with that theorem. I don't care so much if you memorize that number. The main point here is that just to make use of that theorem and to know the theorem exists, right? So by the theorem we just did, H is a subspace of V. And lucky for us, because of that theorem, we don't have to do any other work. H is now a subspace just because it's the span of these two things. How did we tell? By pulling this apart in parametric vector form, we could see, oh, H is in fact just the span of these two vectors. All right? Okay. Let's now transition and take a look at today's participation question. So let's see. This is participation day 13, I believe. Yeah, participation day 13. I'll go ahead and share my screen. Share screen. Here we go. All right, should be sharing my screen. Participation day 13, we're told let the vector space V equal R3. All right, so our vector space is R3. Let H be the set of these vectors x, y, z such that x plus y plus z equals 1. In other words, x plus y plus z equals 1. That's an equation for a line in R3, right? So you can imagine, like we had on the board, sometimes we can have sets of vectors, which is just a line in the space. Just like we had that example where that H was just the line of the y-axis, all right? So H here is the line. It's all the vectors which is on this line, x plus y plus z equals 1. Is H a subspace of V? Well, we can kind of check right away. We know to be a subspace, it has to have the 0 vector. Okay. Well, what is the 0 vector? That's when x equals 0, y equals 0, z equals 0. But when x, y, and z are all 0, does that satisfy the equation? No. 0 plus 0 plus 0 does not equal 1. So the 0 vector, because it does not satisfy this equation, this line, if you graph it, doesn't pass through the origin, right? The 0 vector is not on this line. But because the 0 vector is not in H, that's already enough by itself without doing any other work to see that H is not a subspace, right? So it's not a subspace because it does not have the 0 vector. So we can go in and we can type, is H a subspace? No, it is not. H is not a subspace of V. Right, and that's it. Okay, H is not a subspace of V. Why? Because the 0 vector is not in there. Okay, so that's going to cover everything for 4.1. We have this basic notion of what it means to be a vector space, this basic notion of how to determine if something is a subspace. As we continue in chapter 4, we're going to talk about other weird examples of vector spaces. So far, all we've talked about is R2, R3, R4, right? What about other vector spaces? Are there other vector spaces? What do they look like? How do we solve them? That's what we're going to be talking about next as we continue in chapter 4. So that's all for today. If you have questions, please, by all means, email me. Otherwise, office hours, Tuesdays and Thursdays at 6 p.m. Yes, that's it. Best of luck. I will see you tomorrow.